Hey guys, welcome to Math Busters. Today we're going to be going over partial fractions. Get some food and let's get right into it.
So the thing that we'll be talking today is partial fraction decomposition. And let's dive right into it. The first practice problem we're going to look at, and I'll explain it throughout the way, what exactly we're doing. So we want to find the partial fraction decomposition of this function right here. F of x equals 5x squared plus 16x plus 17 over 2x minus 1 times x plus 2 times x plus 3. Okay, so the first thing we want to do whenever we're approaching a partial fractions question is split and define it. So what we're going to do is we're going to ignore this 5x squared plus 16x plus 17. We're going to ignore that for now. And you see how there's three terms in the bottom here. We're going to do an A, we're going to do a B, and we're going to do a C. We're going to put A over the first term, plus B over the second term, and plus C over the third term. And what we're going to do is we're going to do something called the butterfly method, which is when you are adding two fractions, let's say you have right here in the corner, we have A over B plus C over D. What we're going to do is the butterfly method is we're going to multiply the A times the D, and we're going to add that with the B times the C, and the denominator is going to be the B times the D. So that gives you AD plus BC over BD. And we're going to apply this logic over here. So what we're doing is you see we're doing A times x plus 2, right there. And we're doing the B times 2x minus 1 over the denominator, these two, 2x minus 1 times x plus 2 multiplied. Then we also have, we're adding the C right here. And we do the butterfly method again to get this right here. So
why did we do that?
Why do we do that?
What use does it serve to just like ignore the top part and just do this splitting and defining?
Yeah, so with this defining right here, we're going to eventually set it equal to the top part. And then we're going to solve for A, B, and C. And we're going to solve through A, B, and C in a really clever way, which I'll get to now. Okay, so now we're going to get back that 5x squared term plus 16x plus 17 that we had earlier, and we're going to set it equal to the numerator because this 5x squared term plus the 16x plus 17 already was divided by 2x minus 1 times x plus 2 times x plus 3. So it doesn't matter there. We'll just set the numerators equal to each other. So what we'll get, first we'll solve. We want to isolate one of the three at a time. So the first thing we notice is if we set x equal to negative 3, do you see how right here, since this whole expression right here is being multiplied by x plus 3, if we set x equals minus 3, this whole thing right here gets canceled out, meaning we're just left with the c term right here. So that's what we're doing right here. If we let x equal negative 3, we plug in everything right here. This is the 5x squared plus 16x plus 17 term. We plug in negative 3 here. You see how the a in the 0 and then plus b to the 0? That's because over here they're all times x minus 3. The a and the b term are times x minus 3. And negative 3 plus 3 is 0, so that all cancels out to 0. And then we plug that into c minus 7 times minus 1. We set that equal to the 5x squared plus 16x plus 17 when you plug in negative 3, and you get c equals 2. Now, what we'll do next is case 2. So we've solved for c. We want to notice right here, is there anything we can do over on this expression to cancel out either the a or the b? And yes, we notice that if we let x equal negative 2, it cancels out this a expression by making it 0, and it cancels out this c expression by making it times 0 through the x plus 2. So this is case 2 right here. And then we set it, since we set the top equal to the 5x squared plus 16x plus 17, we're gonna plug in negative 2 there, and then we're gonna set it equal to plugging in negative 2 to the a plus b, the b and c term, and then we'll get this. We see how the a times 0 and c times 0, that all cancels out, so we get negative 5b equals 5, b is negative 1. Cool. And now the last thing we want to solve for is the c. So we already know what a and b are, but we want to figure out how can we isolate the a and the b. And the key thing here that we're going to do, we're going to solve for the a. We want to figure out how are we going to isolate the b and the c. And one thing we can clearly notice is that b and c are both times 2x minus 1. Meaning if we wanted to cancel these both terms out, right? We wanted to figure out what subbing in x makes 2x minus 1 equal to 0. And that is 1/2. So that's why you see right here in case 3, we're setting x equal to 1/2 such that when we plug in 1/2 over here, we are getting right here, b times 0 plus c times 0. So again, we plug in 1/2 squared into the 5x squared plus 16x plus 17 term. Over here, we get 41 over 4. And then we figure out these two b0 plus c0, they all cancel out. So we're left with 105 over 4 equals a times 35 over 4. A is 3. So putting this all together, we are going to get, this is our original expression we have right here, a over 2x minus 1 plus b over x squared plus 2 and c over x plus 3. We plug in the values we get, and then this is the partial fraction decomposition right here. And notice that the key thing we want to realize here is that the whole process, we set a over first term, the first term of the denominator, plus b over the second term of the denominator, and plus c over the third term of the denominator. Then we use clever tricks to make the 2 out of the 3 variables cancel out, so we can solve for each one individually, getting this.
Does this actually equal the original answer?
It does. If we add all these up using the butterfly method, it will give us this expression right here. 5x squared plus 16x plus 17 over 2x minus 1, x plus 2, x plus 3.
Okay, but what if it's something like 5x squared plus 3 over x plus 2 squared? How do you split that up?
That's what the next question is. So I'll get into that right now. Okay, so we're going to look at something a little bit different here, which, of course, when you have something that's not a power of 1 in the denominator, things change a lot. So, question 2, this will answer your question as I'm going through it. Let's look at question 2. Write as a sum of fractions. So we have right here the function 3x minus 1 over x squared plus 4x plus 4. So simplifying this, it's 3x minus 1 over x squared plus 2 squared. So one thing I want to notice here is you can already see right here, we're not doing the typical, first term times second term. Because if we had done what we did earlier in the question, it would be a over x plus 2 plus b over x plus 2. But since we're dealing with something that's not a power of 1 in the denominator, we're going to do something called the power increment rule. I gave a quick example right here. Let's say we have x cubed plus x squared plus x plus 1 over x plus 3 times x plus 3 times x plus 3. Right? So what we're going to do is we're going to say a over x plus 3, then b plus x plus 3, and then we're going to do 1, which is the power on this expression, plus 1. So the power is now 2. And you see how we're incrementing power of 1, like we're plus 1 right here. This is what you kind of need to do if you have something that's not a power of 1 in the denominator, if it's greater than power of 1. So we're going to increment here. Why is that? It's because whenever this expression is squared, or more.
Why do we have to increment it by 1? Why can't we just do like ax plus 3 plus like, I don't know, cx plus 3 cubed or something like that?
Cx plus 3 cubed. You see that the whole reason why we put the power plus 1 in the denominator is because, like, if we had done the a over x plus 3, a over x plus 3, a over x plus 3, everything would cancel out, like, initially if we ended up solving everything, because the x plus 3 the denominator, it's all the same term. So you see how, like, above over here we had this term right here, they would all cancel to 0 if we plugged in the same thing over and over and over again. So that's why we got to increment it to change it up a little bit. Okay, so now let's look at this expression over here. So this simplifies to 3x minus 1 over x plus 2 squared. So obviously you have a over x plus 2 plus b over x plus 2 squared. Now we're going to use the butterfly rule that we talked about over here. A over b plus c over d is ad plus bc over bd. So once we plug that in, we're going to get ax plus 2 squared plus bx plus 2 squared over x plus 2 cubed. The thing we want to realize here is the denominator, this is what we want to set it equal to, remember? But remember, we want to set the numerator equal to the numerator here. But that only works if the denominators are the same. We can't set it equal to this right now because the denominators are completely different things. One is x plus 2 squared, one is x plus 2 cubed. So what we're going to do is we're going to multiply this expression, 3x minus 1 over x plus 2 squared times x plus 2, so that we can get that x plus 2 cubed in the denominator. That's what you see right here. We see a x plus 2 squared plus b x plus 2 squared over x plus 2 cubed equals 3x minus 1 x plus times x plus 2 over x plus 2 cubed. And you see how since there's the same denominator here, we can set the numerators equal to each other and eventually solve a and b. And that's what we do right here. We set the numerators equal to each other, and we all realize there's a common pattern here. You want to simplify as much as possible, and that's why, since you see everything is being multiplied by x plus 2, we're going to divide by an x plus 2 to both sides. And we get this simplified equation right here. A times x plus 2 plus b equals 3x minus 1. This is the left side.
Dividing by 1 over x plus 2 can't remove a solution?
It won't, because remember, we added a solution here when we multiplied by x plus 2 to both sides. So when we just divide that x plus 2 over here, we're just taking out that same solution we added. So it's not really affecting that. Okay. So next what we want to do is, as we did earlier, we're going to do cases. So what can we do to make this a term 0 so that we're just left with b? Sorry, what do you think?
You can just plug in -2.
Yeah, that's right. So if we plug in -2 right here, it's a times 0 plus b equals 3 times -2 plus minus 1. We do that right here. Solve, b equals -7. Now, given what I've told you, what can we do now for case 2?
Just put b back in and just solve for a, because it's a linear equation.
And would you think it would be easier to, how would you solve for a? Give me an explanation.
So you just plug b back in. It's just ax plus 2 is equal. Oh, I see. You have to
Yeah, see,
set. It's
yeah,
two variables.
there's two variables here. That's the key thing. So what we want to do is, instead of just putting b in and solving, we have another case. That's why we set x equal to 0. And 0 is the best benchmark here because if we set x equal to 0, that means like it's just 2a minus 7 equals -1. Pretty clean numbers. 0 is always a good benchmark to use. So as I mentioned, a times 2 minus 7 equals -1, 2a equals 6, a equals 3. And realize the reason, Akhil, that we can't just simply solve this is there are two variables here. We would have a unknown and an x unknown. And we only have one equation. If we have two unknowns, we need two equations, meaning that we need to use another case. Does that make sense?
Yes.
Cool. So what we're going to do now is we're going to put this together. We already know a is 3. We know b is -7. We put that together. We get a over x plus 2 plus b over x plus 2 squared. We plug in the values, and that is this right here. 3 over x plus 2 minus 7 over x plus 2 squared. And that is the partial fraction decomposition.
I hope you like seeing on how we can split fractions into multiple parts. Subscribe, like, and share this video, and we'll see you next time.